Hello everyone and welcome to my session today on monitoring PgVector RAG agentic applications. I am Jayita Bhattacharyya. I am a data scientist. I currently work at Deloitte USI and I am based out of Bangalore, India. Apologies that I couldn't make it in person this time and thanks to the committee on arranging to be presenting virtually. So on that note, let's get started. We're going to be covering a whole bunch of things today from how, as it is, I'm sure most of you attending this would be aware of what RAG or retrieval augmented generation is and how is it different than the traditional normal databases that we had. And obviously, since we are talking about databases, what better than Postgres and how you can convert your normal PostgreSQL databases into a vector database called with an extension called PgVector, and we're going to see that how you can plug this up with agents, and there needs to be a layer of monitoring and observatory tools where you can bring your production systems, you can track all the traces that are going down. We'll be deep diving onto those things, and of course I have a bonus section for you where I'll be discussing about Timescale, which is a time series database company which has open source two very great open source libraries on top of PgVector called PgAI and PgVector Scale that can help you build scalable applications for your production use cases. And of course, what is a conference of fun without demos, So obviously we'll be having demos for all of these things that we discuss and some next steps and resources that I'll be sharing up that you can go in and start up from there. So yeah, let's address what traditional databases versus vector database happens the scene around. So obviously everybody knows how traditional databases work. We go for a SQL search query where it is supposed to hit the exact match and it gives me out that particular information out of it. Say, for example, if I have a name, ID, and age group kind of thing, and I want the age groups from 25 to 30 to be selected. I write the SQL query for it. It goes into that particular index. It gets those rows where it matches the criteria, and it pulls out the information for me. So this is how exact match works in case of our traditional vector databases. In vector database, we deal with a factor called similarity search in and around what are there. So if I say that, can you get me the age group for people falling under the age of 20s? So that would go into the database and search for wherever 20 is appearing, 21, 25, 27. So all of those things would come up. So this is a similarity search. It's not an exact search, but a similarity kind of search. Had I been saying that only get me age of 25, that would have been an exact match and that would come out of it. So if you see this diagram here, it shows you that, not just a structured data that has a tabular format. You can also have your the utility of vector databases is that you can get your unstructured data of, say, any kind of document that you have, or say, for example, even with your structured databases, right? In a table, you have millions of tables that are present. It would be split into chunks first. Chunking is a process where I'm sure people would be aware by now. There's so many things floating around AI these days. So it would convert into small, it would take certain bits and pieces of the table and convert it into embeddings. Embedding is nothing but the numeric representation of the textual or any kind of data that you have that the computers or the algorithms understand, and it would be fed into the PostgreSQL database in this scenario, since we are onto discussing onto Postgres. And similarly, the user query that also comes in, that also gets converted into embeddings, and we go in for a vector similarity search. So whatever the user query comes in, we get to the searching where relevant things are found, and those relevant chunks are got here, and those are say, for example, I got a match in index in row number 5, I got a match in row number 50, and then I got a match in row 150. So all of these data is scattered, but these are the relevant chunks that I need, and these are accumulated and fed to the LLM, and then the LLM is able to generate me a good response that I can actually, as a human, I can interpret that, okay, actually this is the answer. So this is how the exact RAG workflow goes around, and if you're designing, you can also follow the same thing. So PgVector is the extension on PostgreSQL that helps us convert a normal SQL database into a vector database, and it is this. So if you can see here, these are the objects that get into the embedding model and convert it. And unlike other unlike other vector databases, say for example Pinecone, VV8, and all of those that are present, they have so whenever I think of designing a RAG application, or I need to go to a vector database, I have to set up something, some other instance, and get all my data there. The utility of using PgVector is how without having to go to some other instance, I can in and around within my Postgres, I can set it up. It's just an extension that I need, and it will add up the relevant columns for me and has stored the embeddings there, and from there the match can happen and I can get my answers out of it. So this is how the PgVector works, and I think most of you would have been trying it out with the buzz around AI these days. And if you are a Python developer like me who loves to, incorporate things, then PgVector Python is a library that helps you get in that PgVector extension onto your Python. It uses SQL Alchemy and is very easy to incorporate and work around with your Python applications. So yeah, I think by now everybody is buzzed around in the world of AI with agents and what exactly agents are. And we of course know James Bond to be the famous agent. In terms of AI, it is something that it can take autonomous decisions. It can collect your data. It can perform operations onto it, and you don't need to define those formulas or algorithms to take up those instructions and work around with your data. You can just in a natural language format tell that this is what's supposed to be done, and the agent will go on and carry forward those instructions. It would bring out actions out of it. Say, even if it could be something very simple from adding two numbers, it could be something very complex to going on to some server and pulling in data, then transforming it, and it could be any n number of use cases now that we are seeing, and that's where agents have been helpful to us in our workflow and productivity into our use cases these days. So on that note, you must be wondering that, since agents can take decisions, agents can go about and perform tasks, has AGI been achieved, artificial general intelligence, that is the considered as the human level of thought process that it has been made up. That's not true, but not, I won't completely disagree as well. To some extent, it has been achieved, I believe, and because if you see the number of autonomous use cases that we are getting forward to, and with this co-pilots and coding assistants that we get, so a lot has been done, but still there is room for improvement, and that's where we still have work to do. So we are still having hard time vibe debugging is what I say. So yeah, I mean, juggle around vibe coding, and you will find your own sweet spot. So this was so far we discussed about RAG and agents. Now let's come to how when you take your models into production, what exactly happens there. So when you're taking your models, it's working fine with the whatever compute or whatever performance it shows you on your local system, but it's whole another story when you take it to production. There's a huge amount of traffic that comes in. You have to ensure that same amount of throughput is there is very minimal latency, and you have to give your accurate answers, and you have to make sure that it is scalable even during very hard loads that is there. So taking to production would mean that you have an added things and things to keep in mind, and not just in terms of infra, but also various other things come into question there. So for that, we have to in machine learning, there is a certain amount of things that we look forward to when we deploy these models. There needs to be a monitoring and observatory tool for it, where we track down that what was the CPUs. For example, it could be CPU usage, it could be GPU usage, or it could be like how are my false positives or false negative predictions are coming out, and how my answer evaluation takes place. Suppose say in nowadays this Gen AI and LLMs are there, my answer that I'm giving out to the user has to be unbiased, has to be fair, and it does not be obliged to any harmful and anything of that sort. So these many things come into picture when you are tracking down, and it's very so many engineering teams would set up separate teams to take part into these deploying and production things. But there are simplified tools that we'll be seeing today that come into help for us. So LLM app observatory is something that we'll be looking into today, where you can go in and see what exactly tracing that has been taking place. So you hit an API call, and what goes into under the hood is what you need to track, because somewhere your workflow that you design with agents could get wrong, right? You would not know at what point and where this broke down. So unless you have your whole stack trace to debug where exactly it went wrong, it is the only way good for you. You would have certain metrics set up which would give you that this is how the performance is going on, this is how the throughput and latency and error rate is coming out. You would have a proper logging system and evaluation, and all of this is very easily can be set up, other than hiring a whole another bunch of team and doing manual function tasks at all times. It can be easily set up via this excellent open source tool that we're going to talk about today, called Langfuse. It is built by it's I think 2 years old now, and when I saw it for the first time, I was in love with the UI that they have. Very user friendly. If you're not even coming from a coding background, even if you go on and see that, you'll be able to understand how what's happening, and that's how simple it is. And you not only just it's setting up also is very simple. You just have to plug and play some of the things, and it's very easy to do. We'll be seeing that today. So there are certain good things about LLM observatory tools such as Langfuse. It gives you the management of your traces and sessions and all those things. Along with that, there is prompt management. Since we are dealing with Gen AI applications, so we would also have so prompting is an experimental process. I say you wouldn't know what prompt works at very first, but you would know it by the 10th or 20th iteration. You would know what works. So that amount of tracing is needed, that what worked for the first time, what worked for the second time, what worked for the fifth time. So that whole history management can be done through this, and it's not that just the parameter tweakings that you're doing. So it has many other sessions and versions to it that you can manage your prompts very easily. Along with that, you can also set up an evaluation metrics. So if you have a ground truth of your what can be the answer, and you what the bot predicts, so that way you can set up a scoring system that this is what I'm looking for as a threshold, that any answer beyond this threshold should be considered good, and below this there's still room for improvement. So on and so forth. Various metrics and evaluations can be set up so that your system goes into more better trained version of it. Uh, so you can deploy, since it's open source, you can deploy it onto your own infra. And the very good thing about LangFuse is it is totally on board with Postgres. When you're deploying onto your infrastructure, you can keep it is compatible with Postgres to be done, and you can deploy it onto your local using Docker. And also, if you want to go on to Kubernetes and go onto your K8s to deploy, that is also possible. So all of it is very self-hosting is very easy, and you can easily plug it up and go about it. You don't need there's a cloud version that we'll be looking into today, and for ease of simplification. But yeah, additionally, you can go forward with the self-hosted version. So yeah, let's jump onto the demo, and let's see what we. So let's start with the demo, and we are at our VS Code, and I have my folder here which we'll see how how we execute it. And the very first step is so I'm in Python and I have my requirement txt file. I install the required, so I'm going to be using LangChain, and along with that I'm going to be using all free and open source resources, so nothing at all here needs you to for any payments or any third party things to do. So these are the necessary LangChain libraries that you will be needing. I'm sure you must be knowing that LangChain is a LLM orchestration platform which lets you build RAG applications. Any search and retrieval systems that you want to build with, you can build with LangChain. They have that abstraction layer where you don't need to build things from scratch. You can or very we'll be seeing how you can implement it here. And LangChain Grok is a library which helps us inference using Grok. So Grok is a company which has hosted over a couple of open source LLMs. So maybe I can show you the ones that we are going to use here. So here are some of the supported models that Grok has. If you go to Grok Cloud and you can acquire a key, there'll be obviously some minutes, so there'll be a limit on the number of calls that you can make per minute, but that is a very big number. You don't need to worry much about it. So we're going to be using Llama 3.18 billion parameter model here, and you can see that all of these models are open source models that are hosted here, and you can choose any of them and go about. We'll see how we have integrated it. So next is our embedding model. We'll be using a sentence transformer here from Hugging Face, and then we have our LangChain Postgres library to be installed, which will help us communicate with Postgres. And second one also does the same, serves us the same purpose of PyCogs2 binary, and of course Python.env file for our install having access to our environment variables, and LangFuse for the observatory and monitoring that we discussed. So once we have this installed, since I already have it installed, you will see that maybe I can clear it out and maybe let me run one more time. So I have my virtual environment running on this folder, and I can go ahead and run it, and you will see that since all of these requirements are already satisfied, it shows up like that. So next step will be to go ahead and do a Docker Compose up. So here, this is my Docker Compose that will pull in the PgVector file, and I would have my DB running in there. So, with that I can, so these are some of my DB username password. These are all dummy things, so don't worry about it. You will have to mention the port and the volume that you're gonna be using for. And so if you see my Docker desktop, it has this running here, and yeah, this is the container and image and everything is running here. So with this I'm able to host the DB instance and let it run. Next up is my environment file. So this is an environment example file that I have for you. You can go ahead and change it with .env, and these are the DB details that we would need, PgVector details that anybody starting up with the database instance would need it, and followed by you would need the Grok API key that I was talking about, and Then of course LangFuse. So let me show you how you can get the LangFuse API keys. It's very simple. uh, you could just go here, go to LangFuse and go to cloud.langfuse.com, and just there you will get these options where you can add new organization, you will create it and you can set up that. For me already I have certain installed already, so maybe I can show you. If I go to one of these projects, this is how the traces look like, and we're gonna see how this came up, and subsequently when we hit it also live, how will it be appearing. So this is how you can go to, keys and set up your keys there. It's very simple. It's very user friendly interface that you have here. This is the cloud hosted version. If you want, you can go ahead with your own hosted version as well. LangFuse has a very great documentation that you can go through here, and you can learn about it, how to do it. It's pretty friendly and very good user community that they have here. You can go ahead and maybe contribute to it, as it's open source. All right, so here we have our PgVector connection string that we have, and then of course this is an optional parameter. So LangFuse gives you an option to, how many traces were there under one session. You can, if you want to track that, that can be done, but yeah, that's optional for now. And this is a simple text file that I have. This is just to show you the art of possible, how you can do it. So instead of text, if you want any CSV files or any SQL tables that you have, all and everything is possible here. It's open to you to explore. So I have just a simple text file here which says what is PgVector and how do you use it, and what are embeddings, what is LangFuse, what is RAG, and all basically about what our demo and talk is today about. So it contains information about that. So this is very basic kind of a text file that I have. You can change it. So this will act as our base data that we ingest into the pipeline. So that's why I was showing you that one. So this is our main app.py file, and that's how you get started with. You have to import the libraries that you want to start up with. That's the simple basic thing that you do. We're going to be using tools and agents. That's why we integrated these, and we'll see how we can leverage these. Next up, you do the environment variable setup, and then you can maybe, initialize your LLM. So as I mentioned, I'll be using Llama 3 8 billion parameter model, and then I will also plug it up with the LangFuse handler, because that's how I'm going to track whenever this LLM is being called, what is the stack trace going into it. And as I mentioned, we'll be using sentence transformer, all mini LM L6 to convert our text into embeddings. And here I have defined that. So Hugging Face embedding will allow me to do that. And yeah, this is where we had initialized our PgVector connection, and then I can go ahead and I'll read my text file, and then this is the chunking process that we do. So I have a recursive text splitter chunking process of chunk size 500 and overlap of 50, and that's how it's going to be breaking up and showing me that thing. And we'll see how our first chunk looks like, and then you can convert these into embeddings. So you take these chunks part by part and convert it into embeddings, and yeah, that's how it gets stored into the database instance that we have. So the beauty of using PgVector is that if you already have your existing SQLs to be used here, you do not need any other vector database to go on to. We'll be seeing that in our next segment as well, when I explain you about PgAI and PgVector scale. Similarly, you can just define the vector store, and it gets stored into that same Docker instance that I was showing you here itself. It gets ingested and stored up. And So like that, you do not need any other thing to be for storage purposes. PgVector will is just an vector database that serves you the purpose. And then we can set up our retriever, which will fetch us the top 3 relevant chunks matching to our user query. So here we have kept a top k of value 5, 3. You can ideally, based on your use case and compute, you can decide on that sweet spot where you want to land this number to. And then you can so here is the tool that we want to leverage in this particular use case. So it is retrieval tool, and we'll be using the retriever tool. We give it a name and we give it a description. Mind that this is very important whenever you are working with tools and agents. It's very good practice that you give it a name and a description, so that when it goes to the LLM knows that what is the purpose of this tool that you are using. So here we have named it knowledge based search, and we have mentioned that searches and returns information about so and so. So this gives it the LLM a starting point that what exactly this tool does. Next up, we have a prompt for our agent. So this is something pulled from so Harrison Chase is the founder of LangChain. He has already written a very good prompt which can work with agents and tools. You can explore that maybe, and that's how we're gonna use that one. So in my tool, I'm passing in this retriever tool that I already defined, and then I'm calling an agent which will take in 3 things. First is my LLM, second is my tool, and third is my prompt. So these are the 3 things that it needs to make the decision of which one and where to execute which one. So here, of course, we used just a single tool. However, in your production or say complex applications, you would have more than one tools, and that's where the beauty of agent lies, that it has the capability that based on the user query, it takes the decision of which one to trigger. And we have our agent executor, which is kind of an orchestrator that takes in that which one to which tool to be called and which agent to be called. So we pass in those parameters, and then we have to just execute it. And here in the response, I just say as an input, we give a query. So here I'm asking what is RAG, and in the callback, I just pass my langfuse so that whenever this is invoked, it gives me the entire stack trace. So maybe let's run our code and see what it does. So maybe I'll just run it. Just pardon me for the warnings that come up. I know I have to fix these and I have to use some updated versions of Hugging Face embeddings and other subsequent classes, but yeah, just bear with me for that. So let's see what it gives us. It may take a while or two to give us the answer, I think. Okay. So this is one of the chunks that it pulled. So page content is that chunk that it pulled up. Along with that, so we gave a chunk size of 500 and an overlap of 50. So this is what it picked up. Along with that, it gives us the metadata as well. And then it gave us the answer here. If you see, it gives us that RAG combines retrieval of relevant documents with the generation by a large language model. Okay. So here, if I go to my okay, so maybe I can just refresh so that I get the latest call. So if you go to so from here, maybe we can go, yeah. So this is one of my organizations that I created, and within that, let me see, this is okay, PgVector RAG agent. Okay, so I have my PgVector RAG agent, and I go to a RAG agent that I have. This is one of the projects, RAG agent, and I go here and I see that this is the beautiful UI which shows me that how many calls I made. So I made 3 calls to the agent executor, and what was the model cost. We are using open source model which we did not pay for, so it shows me the tokens that were used, but cost was again 0. And then it shows you by what time did you do that, And then okay, this is again the usage cost and everything that isn't valuable to us. Only token count might be valuable to us. So these are there, and user consumption per user, how was the token cost and things like that. If there was latency, what was it, P50, P95, how was that rated? And these are some of the details that get into it. So this is beautiful, when you have to debug your or maybe present how your model is performing over time, how your use case is performing over time. So these kind of infra information becomes very helpful to us. So okay, let's go into one of the traces and let's see what it has to say to us. Okay, so you will see that this was the one that I just triggered, and it came up here, and it shows me certain other information as well as to what was the environment, latency, tokens, and etc. So let's go into this stack trace and see what it actually has to tell us. So this is the two. So it gives me the entire output stack that it went through. What was the calls that it made to? First, it went to tool, and within tool, it got the query, and then it was invoking. So as I mentioned you, right, when we call the tool, the name and the description becomes important because that's what goes into the LLM. Then one by one it came up to other subsequent actions, items that it has to take, and response, metadata, and all sorts of things that will be important to track how our performance is happening. So all of these were triggered, and you can maybe go into any of those and see. So vector retrieve, store retriever gives us what was the exact chunk matches that happened, and how was the what was the page content of those. So that way it shows us. So bunch of things that we can go through here. One good thing, as I was mentioning earlier, is that okay, so there is sessions here. However, we did not set that up. But if you want, you can set it up. They have a beautiful demo being showcased here that you go a certain number of traces coming under one session. You want to keep track of that, you can do that. And there is of course observations, so it will show you what was the chat grok. So wherever I have my handler mentioned, the callback handler that I had mentioned earlier. Okay, so here I have my callback handler here, so langfuse handler. So it will keep a track where all this chat grok was called, and that's how it is able to get me these observations. So, okay. So we do not have our scores set up because we of course did not, as I was mentioning you while showcasing the PPT, that you can set up scores where the what the ground truth is, and you do a similarity search between the predicted answer and your ground truth answer, and you can keep a threshold that above this is what we consider good answers. There are many other parameters as well. If you go through this demo here, they have showcased that. Along with that, they also have evaluations, so you can keep a human annotator who says that what is the good answer, what is a bad answer kind of thing. And along with that, you have an LLM as a judge coming up. That LLM itself, after it gives the answer, you have a good prompt to say that whether it was concise, whether it was fair, relevant, and all of those factors that you judge an answer on, you can do that. So that is pretty much it from the demo perspective. Section, as I promised at the very beginning, I'm going to be discussing about two more libraries which are open source, and they add great value to your production grade application that you will be developing. So let's get started on that. So the first up we have PGAI, which is by a company called Timescale, and they have these certain added features on top of PgVector that PgVector already provides. They have built a layer on top of it, which allows you to get started with automated vector embedding generation, embedding pipeline management, support for multiple embedding models, resilience and error handling, and of course, you would have a bunch of LLMs to integrate your application to. So essentially, if you want to create automatically, you want to create and synchronize your vector embeddings from Postgres data and say for example Amazon S3, then it's very easy to set it up using this infrastructure. Because what happens with vector databases is that it might get out of context, or say it might you need to time sync it up. So to avoid that and overcome that challenge, automated embedding generation is something which is really helpful for you. And this picture here is from one of their timescales blogs. Do read those blogs. I really suggest everyone reading them. You can just it's very beautifully written, and anybody starting up can relate to understanding that. And if you see here, from a DBA or a full stack engineer who handles only the data part of sites and into the tables and database managements, how you can just leverage PgAI to become, along with your existing role as an incorporate AI into your solution and become AI engineer as well. So essentially, on top of whatever PgVector provides, the semantic search, PgAI and PgVector Scale are the two libraries that you can leverage to, ship your production-ready solutions, which would also have, say, so also they have a bunch of support for batch processing, for say built-in if your model fails at some due to some rate limits or anything. So it's very common into LLMs. When you're dealing with LLMs, they can go out of context. Your context window can be reached, and after beyond that, you are not able to process it. So that's where you can, come up with solutions. You have some exception handling there, so you don't need to explicitly be writing those. PGI can handle them for you. And it works with there are ways that you can set it up on Timescale Cloud, or you can, as this is PGI is an open source library, you can, as it is, take into your own solutioning and make use of it. You can use it with Supabase or Amazon RDS and many more cloud providers, or any service that you wish to do it with. So this is a general PGAI, mainly the vectorizer that helps us do the automated embedding generation is what this architecture explains us. So you already have your Postgres database sitting there with the source table and work queue and embedding tables that you create via the embedding model that you have. And now you have your vectorizer, which helps you just to incorporate these things onto your existing bunch of things, that helps you do chunking and maintaining your embeddings from time to time without you having to write or update it takes care of that portion of it. So PgVector can automatically create update from a source table using work queues and configurations tables housed in, say, your normal PostgreSQL itself. The embeddings are created in an external worker that interacts with the embedding services, say for example OpenAI, or for instance we'll be looking at an open source library which we incorporate with PGAI Vectorizer. So this is a basic architecture of where exactly the your database, your application, and your vectorizer sits. So the architecture consists of an application you will be writing on top of your PostgreSQL database, and stateless vectorizer workers. The application defines a vectorizer configuration to embed data from sources like Postgres or S3. The workers read the configuration, process the data queue and into embeddings and chunk text, and writes the results back. The application then queries the data to power RAG and semantic search. The key strength of this architecture lies in its resilience. The data modifications made by the application are totally decoupled from the embedding process, It ensures that the failure in embedding service do not affect the core data operations. So it's very, very effective into production grade where you do not want things to fail and everything is being taken care by a backup or a fallback mechanism that you may call. Another very good library by timescale is PgVector scale, which is also an enhancement to the existing PgVector. So the capability that PgVector scale provides is that you have a high performing, more faster search capabilities. So there are different types of searches that you can go through, not just cosine similarity. There's a bunch of many indexing processes that can happen, and that's what PgVector scale implements. And you can have a higher recall rate and efficient time-based filtering. It will also leverage advanced indexing techniques such as the disk ANN inspired indexing to significantly speed up approximate nearest neighbor searches. So a bunch of capabilities that are present there, and I'm just scratching the surface, and I leave you to explore more. So let's jump into a code where you can see PGI in action using Olama and Docker.
This is an implementation of PgVector using Olama. So Olama helps you with you can have your models, or say you can run large language models, any it could be small language models also, both embedding as well as the generation models into your own local system. You can download the app or run it through Docker, as in this tutorial shows. You can run it through Docker. You can also, or you can host the self-hosted Postgres instance. Along with that, you can also go with the Olama based vectorizer, and that way you can perform a similarity search, and without having you to go for closed source ones such as OpenAI or anyone else. So let's look what's going on here. So as it mentions that you would have a Postgres deployed image with timescale and PGI extensions installed, which is this one. It will help you do that, and you will have a PGI vectorizer image working, and that is this one. And then you can have your Olama image to host embeddings and large language models. So you can so once you download your Olama, you can just download Olama. You can search olama.com and then download the software from there, and then you will have your localhost 11434 running. And you can also for this instance, you do not need to download it. Here you can run it through Docker, but additionally, if you want to execute it, that is something you can do. So this is your Docker Compose file, and you can subsequently do Docker Compose up -d db. So your db will be running there, and you can then install PGAI into your database using this command here. Uh, and then you can go and start the vectorizer worker and Olama to via this command, and then you're good with all the things on the setup is done. Now it's time to create and run your vectorizer. So you can run some SQL commands here. First, we go ahead with creating a blog table which has an ID, title, authors, contents, and metadata JSONB. So all of these you can mention the types along with what exactly you want to create it out. And then you can go ahead and insert some values onto it, and these are very basic things that you have. You can consider it any SQL database that you will be creating out of it. Now you can create a vectorizer which would take in your embedding model and convert these text into embeddings. So this is how you write it out. You first give it a regular class instance, and then you load the column that you want to convert. So contents is the column that we want to convert it, and the embedding model that we are using is nomic embed text, and the dimension is 768. And along with that, we give it that in that same table with SQL, we want another column created where we save these embedding models, embeddings, we save these embeddings of contents into that particular column. So you can, after you run it, you can just check whether your vectorizer got created, and you will get a message of this sort that it is running and the ID is one, or so on and so forth. So with that, you can run a search query and actually test how similarity search works. So this is how you will get the chunk. You need a chunk and the embedding, and you will just go on and say that this is the same embedding model you want to chunk, and this is the text that you are looking for, good food, and the host is again the Olama endpoint is the host, and distance is that you want to measure, that what is the cosine similarity score that you want to decide on. By default it is cosine, and then from where exactly you want, so remember that you stored it in this particular table, and so that table will be used, and with that you just do an order by and limit if you want to. And this is how the result would look like. You have your chunks along with score, which is the more closer match and which is the farthest match. Based on that you would be done, and that's all that you need for your PGAI to be ingested, worked around along with your uh, PostgreSQL. So this you can also, if you want, you can implement it using Python. This whole library is really efficient to have managed these entire things.